This is Daniel with iOS Blackbox Pentesting.
Hey, guys. Hey, thanks for coming. I know it's the last talk, so I appreciate you guys here. This is my first ShmooCon and my first talk here, so I'm really excited about talking. Just to start off a bit about me, I'm an AppSec security consultant with Matasano Security. Previously, I've gotten my PhD in applied crypto. And just a bit about Matasano, we are doing application security consulting, so we test anything that's software, we do pen tests and things like that. We're hiring, so if any of you interested in getting into this, let us know. We are basically across the US and in all major cities up there. Anyone here has had their phone lost or stolen anytime ever? Show of hands. Okay, that's surprisingly few. So apparently people are really, really good at losing their phones. Especially the younger you are, the more phones you're going to lose. So apparently if you're like between 80 and 24, 45% of people have lost or stolen their phones. It's getting a bit better if you're getting older, maybe because they're just more attached to them or something, I don't know. But the point is we're having more and more sensitive data on our phones, right? And losing them is like one of the major things how things can get compromised, not only by actually exploiting software vulnerabilities, but just by losing them. So we have to somehow securing them on the device is a really important factor. So I'll talk a bit about iOS security in general and about what guarantees there are. Then I will introduce the tool I've built to make some things easier there. And then the main part of the talk will be different common iOS vulnerabilities. So we'll talk about what they are, how from a development perspective you try to avoid them, and then have some demos on how you can actually test those things with my tool. iOS actually has some really great platform security frameworks which you can use when you build your own software. So first, right off the bat, all apps are sandboxed. Unless you jailbreak your device, then you kind of lose anything which is there. But that means that actually there's on the kernel level some enforcement. Any system call an app does, there's going to go through a strict filter, and you only can access things which you're allowed to. So there's not just like a CH root or something like this. It's actually a proper enforcement. And on the binary or in the binary execution side, all apps have to be signed, and it's not only the apps, but actually the code has to be signed. So anything running on the device, any page in the memory, before it's executed, there is a code verification check. So copying shellcode on there is much more difficult because of that. And then in the most recent iOS versions, we have all the common protections which we know from our desktop operating systems. We have data execution prevention, so we just cannot execute things on the stack. And we have also ASLR, which is going to make general internet programming much more difficult to exploit. So all these things together are actually the best we can do these days for protecting us from malicious code. And the passcode seems like okay, it's just that somebody cannot take my phone and go in there, but actually ties into many of the core security frameworks which are in iOS, and it's a really important feature to protect the device. So iOS applications, they're kind of two kinds, one could say. The first ones are apps which are fully written in native code. That's Objective-C, C++. You can also use regular C code in there. And the other ones are like web view applications. Like some company says, hey, we also need a mobile app, right? And we have this nifty mobile website already, so let's just make an app which does not anything but have a web view and then display websites in it. So these are actually fairly common also, but they're both native applications. And when we look at those from a pen testing perspective, we try to figure out what is the attack surface, right? And if you see the app is the blue one in the center there, the main path of interaction is the user just interacting with the application, right? So that's user input on the device, entering data. And then most apps also talk to some network service. It can be just a random API, like HTTP API, which you know, or it can be some of them that talk SIP or XMPP or any other protocols. So there's potential for attack there. Then also, if you have ever logged into an app which is switching over to Facebook to log you into the application, there's certain IPC inter-process communication on the device where apps talk each other. So there's influence between applications. And then the last category, like down at the bottom, is about how the app integrates with the operating system and any side effects operations have on the OS, which you may not be aware when you just develop the application and don't look what the operating system does in addition to what you want it to do. And all those things then obviously are prone to physical theft. So for a pen test, you want to have a jailbroken device. And the reason for this is that everything's sandboxed before. So if you actually want to see what's going on the device, you have to jailbreak it. It gives you SSH access. You have a full Unix environment on there. You can see any files which are stored, not only from the apps, but also from the OS. You can see what's running. And the other interesting feature is really mobile substrate. And that's basically allows you to hook into any function which is on the device and pre-compiled applications already. That can be from the operating system, but it can also be apps which are on there. And you can rewrite those apps on the fly, and you can patch them, or runtime patch them. With a nice, which is so basically a lot of tools which are out there for pen tests, they actually leverage this, and they modify things that you can easier access the data. So that kind of covers all the data, all the tests which you do on the device, so which covers what's happening on the device. And then in addition, you need some sort of proxy system to look at all kind of network traffic. So if it's just an HTTP API, you kind of see something like burp. If it's something different, you need some binary proxy, things like that. All right, let's talk about tools. There's a lot of great tools out there for iOS. They're kind of scattered. There's a nice list on the OWASP website, which is pretty good. Gives a pretty good overview of what's there. There's tools for static analysis, and there's also a lot of dynamic analysis tools out there. So when we want to assess an application, you have to get a full understanding on what it's doing and how it behaves along the way. So I'm from a dynamic testing background, so I didn't look at reversing and things like that, but more like trying to understand how to automate some parts of the analysis, which you just usually would need to painfully go through by hand. There was a talk at OWASP AppSec USA by Jason Haddix, I think is his name, from Fortify. They also built a system which is just like a black box system. You just upload your app there, and it tells you, yep, you're good in all these areas, but here you might want to check, and they'll probably sell you consulting after. So this is just the open source version, which does less than what they're doing, but it goes in the same direction. So IDB started off as just being a command line tool written in Ruby, just to find interesting files in apps. And then I decided to extend it a bit and put a GUI in front of it so that you have a better overview of what the application does. It integrates some of the existing tools which are out there already, but there's also some new features, as you can see, which I hope will be useful and hopefully find some new bugs out there. So the goal was to make it just easier to work with all these things. So that brings me to my first demo. I'm going to do the first demo live, and then I'm going to switch to some videos later because I need to show the the iPad screen on the screen, and it's going to be a bit fiddly if I do this in real time. So this is basically how the app looks like. On the right side, you have some features. Oh, you don't see that? Well, no, that's interesting. Oh, to the left. All right, that works. No, I don't see it anymore. I'll figure that out. All right, so on the right side, the screen's a bit small from resolution. Here you will have all the tools. On the left side, it's going to be some overviews. So if let me see, menus on my side. So if I connect, there's a menu up there, which you don't see. It's going to connect to the device. And the first thing that's going to happen is that it shows you a screen, which just shows you if all the tools which it uses internally are installed on the device. And if not, there's going to be an install button, and you can just automatically get it on there. So that's installed either from Cydia, or they're pre-compiled with the distribution and the shipping in there. Okay, so when you're connected, you see that down here, connection is established, and you can select an application. So this is going to load all the apps which are on the device. I don't see any of them, so I just click randomly on something. So it basically shows you some information about the application and the bundle ID and some identifiers. And now from a Pentest Setup perspective, there is a preference dialog, which is kind of interesting. So in order to connect, first you can set if you want to connect via SSH directly or via USB. There's something called USB MUX-D, which tunnels SSH through USB. So you don't need to worry about getting both of your devices and your laptop on the same network. It just goes through USB transparently for you. And then you can also set up some port forwardings, which is kind of nice for if you want to proxy something, or if you want to access resources on your laptop from the device. You can just configure all of those things here. So I have like a short video. What else? What comes after? Let me see. That one hopefully works. All right, so I selected a different app here, and I set up a port forwarding for a port. Huh. All right. Let's try this again. Am I on the button there? Yep. Right, there we go. So basically, you can just SSH into the device then on localhost when you have the port forwarding set up, which is kind of useful that you don't have to worry about figuring out IP addresses and so on. It just makes it a bit easier. And then also, I port forwarded port 8080 from my local host to the device. So now you can just set the proxies on the device to localhost. You don't have to worry about opening your firewall and getting the device connecting to your laptop somehow. So I've set that up, and now I'm going, I have burp running on my laptop, and I'm going on the device, and just going to some website, and you're going to see that the request just ends up in burp, even though the proxy is localhost. So it tunnels it through USB back to the laptop. Take a few more seconds, and then, yeah. So that's kind of nice, and makes just things easier to get started with it. Instrumenting sometimes is a pain, just to get your device and your app instrumented. Okay, back to the presentation. So let's talk about some app vulnerabilities. I'm not going to go into too much detail about these, but there's the OWASP Mobile Top 10, just like there is one for web applications. And most of these apps, most of these vulnerabilities actually affect the device directly. And as you see, information storage is actually one of the top things, and securing data in transit, and also in REST. So these are the major things there. I'm going to touch upon them as I go, so I'm not going to go through all of those now. So if you want to look at the app binary, there's some very easy checks you can do just to make sure that, well, that you don't have any of the, so let's do it the other way around. So it's native code, so we have all our nice bugs, which we know. But for overflows, we can have use after freeze, format string vulnerabilities. There's a nice way of specifying %at as a format on iOS, which can lead to code execution. There's a presentation which is referenced here, which you can look up later if you want to. And also, very often we see that app developers store credentials in there that can be like API keys or cryptographic keys for encryption. And obviously, it's not a good place to store this in the binary. You can just run strings on it, and you're going to get all the keys back out. So if you're developing iOS applications, you should take advantage of all the OS protections which iOS gives you. So you have to compile your binary as position-independent code. Otherwise, it's not going to be using ASLR. You can also enable stack canaries. So that's just on the stack. If you have a value on the stack, you write it. The compiler will automatically put a random value in front of that value when it's being written on the stack, and it will check if that value got overwritten. So if you buffer overflow, you will overwrite that value, and the check will fail, and the process will be terminated. Automatic reference counting is in there since iOS 4, and that actually takes care of all the pointer magic for you. So if you free an object or you free it twice accidentally, you can avoid. If you use ARC, you don't have to worry about use after freeze and double freeze and things like that. And again, don't store credentials in the binary. So let's look at a second demo. This is over there. Okay. So there we go. So it's just an app which was selected very previously, and then you click on Analyze Binary, and you get immediately the information how it was compiled. So it checks for position-independent binaries, stack canaries, and automatic reference counting. So you just have a direct indication if the app you're looking at has all those protections. You can look at all the frameworks it imports and see if there's anything fishy there which you don't trust, and then automatically run strings and just analyze what's covered in there. So in a very, very easy way. Something I hadn't have time to do yet would be class.dump-z, which is a nice tool which actually gives you all the class names and function names which are in the app automatically out of the binary. And that's really useful if you want to do more advanced things like mobile substrate patching and things like that. So that's going to be hopefully in there really soon. All right, let's talk about local storage. This is like the big thing. As I've mentioned before, they're all sandboxed, all the applications. So the folder is a private var mobile application, and then there is the app ID, which is assigned by Apple, I believe. It's just, that's the folder, and the app itself can only access data which is in there. But it's also stored in backups. So if you backup your iPhone or iDevice and you don't encrypt it, any malware on your desktop can just get anything which is on the mobile device as well. And since this happens automatically in iTunes, most of you will probably have that on your desktops. And if somebody steals the device, they can just jailbreak it and they get access to entire file systems. So that's like the two major ways how you probably can get to data on the device. So in order to prevent that, let's talk about encryption in iOS. They actually have, they really thought about how to how to secure mobile devices in sense of providing some sort of encryption for it, especially at least in the later versions of iOS. So anything on iOS is encrypted. All files are encrypted, and the file key is just stored in the file system. So that wouldn't be very great, right? Because anybody can just read it. So they're encrypting it using a device particular specific key that's stored in hardware. So there's no way for any app or on the device to read the key out of the memory. But it will transparently encrypt and decrypt that data when you read from the file system. So if you just do an open on a file, it's encrypted before, but it will transparently be decrypted for you. So that doesn't gain you much. So in order to actually get protection from this encryption, you need to set a passcode. And what happens is that the passcode is only entered by the user, it's never stored on the device. And at that point, when it's being entered, it runs through a key derivative function to get a key out of the passcode. And that key is used to encrypt certain protection class keys. And those keys, there are different ones I'll talk about in a second. And depending on which key is being used, the file is protected whether a device is locked or when it's unlocked or in different cases. So basically, the passcode is the only thing which gives you actually security guarantees on there. If you don't have a passcode and you cannot enforce it in your environment, like at a company, then you basically lose all the encryption and security which iOS can give you. The interesting thing is what I should mention before is that just jailbreaking it does not bypass the PIN code. You can bypass the PIN to not get access to apps, but the encryption will still work because there's no way to recover the key without the PIN code, except for brute force attacks. So the data protection API is what you can use to actually make use of those things. And there are different protection classes. By default, nothing is encrypted. I mean, it's encrypted, but it's so encrypted that the OS decrypts it for you. If you actually want to get proper protection, you should use the complete NS protection class. That one locks the file anytime you basically lock the device. Then there are some special cases from boot time till unlock, the first unlock, and so on, which probably have some special use cases where they're useful. So if you're creating a file in iOS, I kind of hate Objective-C, but down there is some code snippet. And if you create a file, you can just pass an attributes dictionary, and you can set the file protection key. And from then on, anything you write or edit in the file will automatically be encrypted, so you don't have to worry about anything anymore. And I guess this is a good point to put like a word of warning. Writing your own crypto is really hard to get right. There may be some people which have like needs for that if you need to enforce crypto in environments where the passcode is not enforced. But then you should really get also a review from somebody who has done that several times before. The general problem is just where do you store the key? If you store the key on the device, then you would still need to store it encrypted somehow, and then you're relying again on iOS protections, which you don't trust because you increment your own crypto. So you would need to write your own key derivative function, or rather use one which is there, and there's a lot of potential to doing something wrong there. So shameless plug, Metasan is running some crypto challenges, which are really fun to do. And it's always good to learn about crypto by doing and breaking things. So if you just send an email to cryptopals@metasano.com, they're going to hook you up with some nice challenges. It's just for fun. Nothing's going to be published. So let's talk about some common ways how data is being stored. SQLite is just in iOS forever. It's just a SQL database which just lives in a file. So people which know SQL, for them it's easy to use. But the problem is, by default, it's just on the file system and it's unencrypted. So if you have an app, you just open the SQLite file and you get full access. So obviously the mitigation here is you just want to use NS data protection classes to protect the file. And that's something like the NS persistent store coordinator, which people usually use, and you can set the same attributes dictionary which we've seen before to protect that. And there's some third-party solutions like SQL Cypher, which are doing similar things, and they're actually not working on the file level. If you have like a big database, you would always need to decrypt the entire file. They're actually decrypting this on encrypting it on a page level. They use sane ciphers, but I haven't looked at the actual thing, so it's not a recommendation or anything like that. Also, if you delete data from a SQLite database, it's probably going to be still in the journal, so you might want to vacuum the database to make sure that it's actually gone. So the second very common thing on iOS are plist files. So if you ever use NS user defaults, which is like the thing to store user preferences on the device, that's going to end up in a plist file. And it's nothing else but an XML file. And there's also binary representation, but you can just convert them using the PL util. And very, very often they're used for keys and credentials and things like that. I don't know if I can read the screenshot. Anybody remember the Starbucks news like a few days ago? Starbucks got like OAuth tokens leaked in files. Maybe, I don't know why they got that much press for it, but this is the path. I just looked through some apps with thinking, hey, maybe there is some OAuth token somewhere, and apparently the path application also stores their OAuth token just simply in a plist file unencrypted. So this seems to be really common, so maybe something worth looking into and pointing out to people. So don't do that. Instead, if you have binary data, you just store it on the file system. But usually plist files are some sort of structure, they're dictionaries, they're arrays, and things like that. So you can use a keychain for that. And the OS keychain is basically, well, it's not really a key value store, it's more like a store for structured data. So you can store also more complex structures. And it just lives on the file system in a file, which is a SQLite database. And the interesting thing is they don't encrypt the entire database, but the fields inside are encrypted separately so that you can enforce different kind of privileges. For example, just as we've seen before, we had how was it called? NS data protection none, and we had complete. And here the similar things, which is ksec attr accessible always, which is no protection. Or you have ksec attr accessible when unlocked, which means only when the PIN code has been entered. And the enforcement is working on the similar level as for the files. There's also an interesting variant, which is called this device only. This actually prevents data from being migrated to a new phone. So if you have, let's say, some credential or some key which is specific to a device which you generate, and you don't want it to migrate over to a different device through backups, that's a way how you can enforce that that's not going to happen. And there's also a feature which I'm not sure many people are familiar with, so-called keychain access groups. It's a way to share data between your applications. So if you have multiple apps, and let's say you have Facebook and Facebook Messenger, I don't know if they actually do that, but if they have a token which authenticates you, they don't want you to log in both apps. So they could use, for example, this kind of mechanism and share and store that secret in the keychain, and both apps have access to it. And the way this is made secure is that every app ID in iOS has a bundle seed and a bundle ID. And the bundle seed is something which Apple generates for you, so they make sure that no two people have the same bundle seed. The bundle ID is just what you choose, so it's just something like com.company.myapp. And anything which has the same bundle seed in the application, in the entitlements, can actually access the same data. So in order to share data between things, you can set this ksec attr access group parameter on data which you're storing, and then any app which has, in this case, the beef1337 prefix can access that data. So that may be a good way if you need to share data between applications. So let's look at some demo for that. Almost, there we go. Okay. So first you select an application. I forgot which one it is. Okay, just some running app, some random thing. And then we can go to the local storage tab, and there's like plist files, and you can just refresh, and it's just going to go through all the plist files on the device, and it also shows us the data protection classes. So plists are not necessarily bad if you could encrypt them, so there you can at least see it directly. You just double click and you open up an Xcode. Similar for SQLite databases, you can see that there is a database, or two of them here, and one of them is actually protected till first user authenticates, and the other ones are not. And then also you can just double click on them, and it opens it in your SQLite editor so that you can browse them. It's like, just makes it very easy to just look for these things and see which data is stored where. Cache DBs I'm going to talk about in a second. You don't have to really worry about those right now. And then there's also a file system browser where you can just browse the app file system manually. So it's real time on the device. You just click on the different folders and you see the apps listed. And then you also get permissions and you get protection classes for each of the files. And then you can rsync the whole app down to your desktop. And I integrated it with Git so that it takes snapshots. So whenever time you click that, you get a snapshot with Git. And if you can see how the app progresses and if it stores data and if it temporarily stores data in between. So it's just you can use your favorite tools to then look through that. So I think that's like really useful to check for all these local storage issues out there. One more thing is coming up. There's also a keychain dumper. I actually use an existing tool called keychain dump, which I got the permission to use by the author. And you can just dump the entire keychain, and you see what's being stored. And you can click on the different items, and you see the values on the bottom there. And this Probably you will find credentials from your email accounts and things like that in there. But that's okay. I mean, they're encrypted in there. But at least you can see what your apps are doing. Okay. So I really like that. So the way to break crypto is not to break crypto usually, right? Bruce and I said that yesterday. You usually find some way around breaking crypto. So if your app has any other flaws, such as cross-site scripting or some sort of SQL injection or something like that, in a SQLite database you can have those things, you can still get the data out of the device because it's encrypted, but when your app is running, it obviously has access to it. So we had this really interesting bug, at least I found it interesting. It was an app which locally cached files. So there was a user which could upload files to a server, or like a group of users, and another group of users could download those files to view them. And it was cached those files that you can read them offline. So if you're in a plane or something, you can read those files. So if you could upload HTML files, and those were stored on the file system. So we thought, okay, so what if we just include some JavaScript in that? And then you could just make an XML HTTP request from that HTML page, and you could open a file URL on the device. And iOS, same origin policy, apparently just lets you read any file on the file system with that. So we would just get the file back from the device by basically doing cross-site scripting on the device. So I thought that was really interesting that it actually works. So whenever you cache user content on the device, you really vary how you display it and how you sanitize it before doing anything like that. Okay, we get to some, the second to last portion is about like some information disclosure. This one's kind of interesting and, well, also a bit boring at the same time. But your app takes a snapshot. When you background an application on iOS, it takes a snapshot. And the reason it does it is just for user experience purposes. When you resume the application, they just want to be snappy, and they want to show you the screenshot right away while your app is still trying to catch up. But that screenshot is stored on the file system, and it's not encrypted. So if you have, I don't know, you have like credit card information or anything on your screen at that moment, when you background the application, it's going to be on your file system in that screenshot. It's a subfolder of your application bundle in like the caches folder, and it's just stored there. So you might want to hide that information before backgrounding the app. Like a really common way of doing this is there's a delegate in the application class, which is called application.enterBackground. And there you can just do anything you want to hide any data which you don't want on the screen. And the popular thing is to just place the launch logo just in the foreground, and then a screenshot will just see that. It will not see any data. There's actually a new feature in iOS 7, which is called Ignore Snapshot on Next Application Launch. And that one, so the documentation says it prevents the screenshot from being taken. I have actually verified that. But what it's meant to do is, again, the user experience thing. If your application always redirects you to a login screen when you resume, and it would show you the old screenshot before, how the app looked, and that looks really bad. That's what Apple thought. So they decided, okay, let's give the app the option of not doing that. So in that case, the screenshot will not be taken and will not be displayed. So that may be something in iOS 7, how to do this. Another thing, we saw the cache DBs already in the list earlier. Basically, iOS by default caches everything which you're sending over the network. So if you're using NSURL connection to request data, like HTTP data, it caches all of those. And it also caches the requests. So here I signed up for some website, and I looked at the cache DB, and they were just passing all the usernames and passwords as get parameters. So everything of those things are in the cache file. And it's not really clear how often those are also being deleted. You can forcefully delete them as a developer if you wanted to, but most people don't and leave it up to the size limits which iOS sets for you. So the recommendation here is a bit difficult because you may need caching if you're downloading big icons or any kind of data, JavaScript, which you don't want to reload every time. But basically what you can do is there's a delegate in the NSURL connection which is called will cache response. And if you tell that to return nil, then it will not be cached. So you can prevent caching that way. Or you can also enforce it on the server side with headers, but then you're still going to have caches of the requests. And the last one is log files, which sounds like nothing much, but then IOActive just recently had a study where they looked at 40 different international banking applications, and 40% of them actually disclosed credentials or other sensitive data of clients in the log files. Including usernames and passwords. And the problem with this is that iOS log files are readable by different applications. So there's actually an app usually you can install on your phone, which is a log viewer, and you can look at those things. So it's not only when your device gets stolen, it's actually other apps on the device which can attack your data this way. So just find some sane way of doing this in development, either by redefining your logging statements or using preprocessor statements, something like that, just that you always know that your log will never make it somewhere in production. All right, let's look at another demo. So the first thing will be the screenshot vulnerability. I just made a small wizard which just walks through the steps to test if it's being created. So it's in the tools menu for this one. So first thing you have to do is you're launching the app. This, on the right side is the iPad. So you just click the launch app button. It just remotely launches it for you. And then, well, this just goes to the login screen. It's not really sensitive, but you can test it on whatever page in the app you think is sensitive for you. And then you just background the app at that point. And when you click next, it says, hey, screenshot found. And then you can just click on it, and it opens up on your desktop. And you can send it to your client as proof of concept or something. There's a log file viewer. Those things have already been there. Xcode has it integrated. But I just like to have it all in one tool. So this uses iDevice syslog, and it just streams the system log file from the device here. It has some code highlighting, and I hope I will get some grep going that you can filter. At the moment, it's just a big dump. But you can see what's going on. You see all the system events as well, but you also see all the apps. So. Okay, so I already mentioned inter-process communication earlier, apps integrating with each other. And so the problem started with Apple not having a proper way of doing IPC on iOS devices, but users wanted to have it. I mean, developers rather. So people started out using the Pasteboard, which is just copy-paste, used for copy-pasting. And then finally Apple said, hey, well, we have all these custom URL handlers, which I'm going to talk about in a second, and let's make this the approved solution for apps to integrate with each other. So these are basically the two IPC mechanisms which are being used out there, but mostly the URL schemes. And you can also share data with kitchen access groups, as I said before, but obviously you cannot send messages, so it's just for sharing data. So the pasteboard has a big problem that anybody can read them, and what Apple calls private pasteboards are not private at all. It's just a matter of guessing the name. So if you know the name of the pasteboard, you can still get access to it. And people are not very good at choosing random names, right? So most likely it's going to be something obvious. And you can also run strings on the binary, and you can just most likely figure out how their pasteboard is called. And then you can just read any data, which they're copying in there. So don't use it for IPC or for any sensitive data. If you're concerned about your users copying things which they're not supposed to copy, you can disable copy-paste. If you override the can perform action handler for UI text view, you can just set it to copy to no, return no, and then no user will not be able to use the user interface for that anymore. URL schemes are much more interesting. They're registered in a plist file, in the info plist file. Up there it's a bit small, but just for test, there's like a Matasano handler. And what always happens when you call that handler is the app opens, and then a certain handler is called. In this case, the open URL handler. And in newer versions of iOS, it actually gets passed in the source application. So that's the application which called the handler, because anybody can call URL handlers. So even in a Safari, you can make a link, you can send it to somebody, or an Oni web page, and you click on it, and it's going to execute on the device. So that's why the source information is really useful. So the problem is, since anybody can call it, there's a lot of malicious input which can come from there, and there's also trust issues, which I'm going to come to in a second. But also really interesting is hijacking, because nobody enforces which handlers you register. You can just put it in your plist file. Apple doesn't enforce if the name has been taken before. So if multiple apps register the same one, they say, well, we don't really know what's happening. So if you're expecting some data to come in from your second application, and like your attacker can just register that same URL handler with the same name, and he may get that data instead of your application. So there's really ways to hijack things. And then there's two interesting examples about exploiting trust, which I've seen actually in the wild. The first one was an app which thought it was a good idea to expose like a configure handler, where you can pass a server and the port number it's connecting to. So you can just have a web page which calls that and sets it to an attacker-controlled server and port, and the next time you log into that app, it's going to send all the credentials nicely to your server without you having to do anything else. So that was great. The second one is more about these web views we talked about before. There's many apps which are showing like a website, and sometimes the website which is being displayed is remotely controlled via URL handler, like a login procedure, which then after the login says, okay, now this app should please go to the login complete page. So that's like fisher's heaven. If you have a banking application and you can just give it a URL which it shows you in the trusted banking application, and you format it like it looks like the original banking login, so I mean, there go your credentials. So basically the bottom line is you always should test who's calling your IPC handler, that you know that it's the app you're thinking about, and you have to really take care that you perform strict input validation there, and don't do this configure thing. I mean, it's just bad. Right, another demo. So this one actually has two of the new features, which hello, here we go. All right, so the first thing is the Pasteboard monitor. Basically, you can add a list of custom pasteboard names which you want to monitor. By default, it's only monitoring the general pasteboard, which is the default pasteboard. So it shows you the current content there, and then we just go on the device. So this is remotely executing an app I wrote, which is also in GitHub, which does nothing but dump pasteboard contents and watch it for changes. So here you can now, if you just select this and press copy, and then it's going to appear in the. But obviously, this is like the user interacting use case, but apps sometimes copy data in the pasteboard programmatically, right? So it's not the user interaction we're looking for. So URL handlers are interesting. I actually wrote a small app which has a buffer overflow just to demonstrate what happens. So here, the URL handler tab can just list you, first of all URL handlers that are registered by this app, and then you can just click on them and specify the rest of the URL, because we don't know the format, so you need to get that from somewhere else. But by just calling the URL handler without any parameters will definitely launch the application. So if you click on launch, I forgot to foreground that there. It opens up the app in the foreground. And since we don't know if there is a vuln, and this is like a non-reversing scenario, so I wrote a fuzzer to fuzz URL handlers. So the idea is that we have here a fuzzer tab where there is this is just some boring basic fuzz strings, but you can add them whatever you like there. And then you specify down at the bottom, you specify the format you want to fuzz. So basically we copy over the handler from here, and we can, at any time, we can put this substitution pattern multiple times in any part of the thing. So it's just going to launch the app, and then it's going to kill it after a while, and then relaunch it with the next input. And it actually does crash detection. It checks the crash log folder on the device, and the first one is a false, and the second one is a true. So crash was detected. So buffer overflow, right? So you're kind of expecting that. And now we can go into Xcode and the organizer to check the crash logs on the device. I'll take a second there. And we see that there is a new one for the URL handler app, and if you look what kind of exception we have, we just see it's like bad access, and we have like 41s there in the address. So we definitely know it's like a very basic buffer overflow. So hopefully we find some apps, some other bugs with that. Right, so the last section I'm talking about is going to be network communication. Obviously, apps are talking to various things on the network. APIs or some sort of other services which are using binary protocols and things. And if you're developing the app and you're coming from a web development background, you kind of have to solve the challenge which the browser does for you a bit yourself, because you have to figure out, do I trust that server which I'm connecting to? And obviously we use SSL and TLS for that these days. So it's just going to be a very brief overview. And sometimes I have the feeling people are a bit confused about what certificates are, so it's just a very quick thing how the validation works. Let's say you're company.com down there at the bottom, and you want to buy a certificate. And at the top you have some certificate authority, and they're not in the business of selling to end users very often. So there is usually some intermediate certificate authorities. And they're saying, hey, I want to resell for you. So they let their key being signed by the CA, which vouches basically that the CA says, hey, I trust these guys. And that goes all the way down until you as a client go to intermediate 2 and say, hey, I would like to sign my domain.com. And they are going to give you a certificate which says, we have verified that you are actually the owner of this. Now, your device is going to have a blue and a red certificate in this case. So the blue one is the one on the left, which you got, and the brown one is another one which your device just happens to trust. And your server has, your server is going to send its certificate and all the chain up, all the intermediate certificate it knows which it got from the certificate authority. And your device is just going to verify and walk along and say, okay, this has been signed by the middle one, and this one has been signed by the blue one. Hey, I know the blue one, so I am trusting this. So this is how this basically works. And the good thing is that iOS does a good job in doing this by default. So by default, any connection which you do with the core framework functions actually check that CA is valid and that it's one it trusts. But it also offers you great flexibility in validation. The good thing is that can make it stronger for you. The bad thing is that oftentimes it's being overridden for development purposes because you have self-signed certificates which are not signed by a valid CA. And you can actually really easily just accept any cert. So basically, this code down here will disable any certificate checking in your application. It just returns server trust, meaning I trust this server as a credential for will send request for authentication challenge. I'm going to love the names. So it's going to return that, and then it trusts any connection. So please don't do that. So the bypassing thing, I mean, in development, it's just useful because you need to connect to your development servers and you don't maybe have a valid certificate. But maybe you can consider getting a free cert. StartSSL.com and others offer you free certificates which are actually trusted. Or you can install your certificate which you installed on your server explicitly on the device, and then it will trust it as well. And you don't have to go through hoops and write code to actually accept this. Another thing to consider is certificate pinning, which actually can make your security stronger if you have like a compromised certificate authority, which is known to happen recently, right? So basically the idea is that your phone knows, hey, I trust all these two certificate authorities, blue and brown, but your application has more knowledge. It knows that its server it's talking to is actually signed by the blue certificate authority because you bought that certificate. So when you make a connection and it turns out that the certificate chain ends up at a brown CA, your app can say, no, I don't trust that, and I don't want to connect. And implementing this may be a bit tricky. So there is some frameworks out there which are helping you with that. Isaac Partners has El Conservatory public framework for iOS, which is useful for this, and OWASP also has some recommendations. So, well, okay, I forgot to click. So IDB has some features for that. I don't think the current version is on GitHub right now because I had some issues with that. The way iOS handles this is that it has a trust store. And the trust store contains the certificates which it trusts. And the simulator, it's really just a SQLite database, and anything which is in there, it trusts. There's an interface in IDB which you can view when you select the simulator. You can select the CA tool, and then you can install certs which are being copied in that trust store, and it will trust it, because there's no other way of getting it in there. There have been some command line tools before. I just thought I also add this to the tool chain here. On the device, it's a bit tricky. There's also a trust store file. But just adding a cert to that didn't seem to work for trusting it. If you install it like the mobile device management style by using a provisioning profile for the whole thing, a configuration profile, that works fine. And that actually also adds it to the trust store. And then deleting it from the trust store will remove the trust, but adding it back will not restore it. So there is some strange issue there. If somebody knows exactly how that's handled, I'd appreciate some input on that. And if you encounter in a pentest an app which actually uses pinning, you cannot intercept the traffic, right? So Isaac has this iOS SSL kill switch, which will just disable these kind of checks. And it's just easy to install. It's a deb file. You can just download it from GitHub. It has been updated to iOS 7 recently. You run it, and then in the preferences, you can enable, disable the checking. So for the future, I would like to add some new features, like a host file editor maybe, so that you can redirect traffic, basically change the DNS lookup to like localhost if your app is using doesn't respect certain proxies or things like that. and then some improvements. At the moment, there's not much error checking going on, so it's probably going to crash a few times if you don't have everything rightly set up. So there's some improvements there, and adding some new tools I've mentioned before. And please let me know if there's any bugs or anything you have trouble with and you want to use it. I'm really willing to help and maybe get some improvements in there and making it like really useful to some people. Right. Lastly, this just in. So we started a CTF together with Square. That was just, I think, 3 days ago now. It's a memory corruption flaws on the MSP430 platform, and it's all browser-based. So you basically can find memory corruption flaws in the browser by hacking a virtual MSP430 microcontroller. So it's really cool, and you guys should check it out. Okay, thanks. Questions? Yeah.
Just so I can remember, does the device have to be jailbroken in order to see all of this data?
Yes.
Yes. Okay.
Yeah. So it has.
And secondly, what kind of footprint does your tool leave on the device itself? Is there any writing, anything that it does to the device in order to get all of this?
The only thing it does, it copies a few command line tools over there, which it then runs. They're just in one folder. So it's just like a few files which are being created in one folder, which is nothing have to do with the application. It's a different folder, so not really anything. And the code is up on GitHub, so the URL is here. Or send me an email or tweet to me if you have questions.
On iOS 7 with the screen switching when you go between apps,
Right.
I've noticed the PayPal app actually blurs that image in the switch and nothing else does. What's the mechanism for that? Do you know?
They will probably blur it in one of those handlers, like application will enter background. They will probably blur the screen on purpose and just do it that way. I mean, I guess for an application like PayPal, it makes sense to go through the hoops to actually worry about that. Yeah. Great, thanks.